Dear students, last time we have seen what are opposing reactions. We have also seen few examples of opposing reactions. Let us see today how can we determine rate constants of opposing reactions. We know opposing reactions involves both forward reaction as well as backward reaction, and therefore when we want to determine the net rate constant of any reversible reaction, at that time we have to determine both the rate constant of forward reaction and the rate constant of reverse reaction or backward reaction. The determination of net rate constant of a reversible reaction is a little bit cumbersome, because as reaction proceeds, the concentration of the product increases, and as a result of that the rate of backward reaction also increases. So many times the rate of reversible reaction is determined in the early stages of the reaction. So without going into the details of that, let us see how can we determine rate constants of the reversible reaction, taking an example of a simple hypothetical reversible reaction in which both the rate of the rate constant of forward reaction and backward reaction are of first order. So let us have that simple hypothetical reversible reaction in which the rate constant of forward reaction is K1 and the rate constant of reverse reaction or backward reaction is K2. Once we know this, let us see how can we determine the expressions for what K1 and K2. What is K1? The rate constant of forward reaction. What is K2? The rate constant of backward or reverse reaction. Let us suppose small a is initial concentration. Let small a is initial concentration of A. After time t, x moles of A decompose and gives product B. So the concentration of A after time t, the concentration of A after time t is A minus x, and obviously the concentration of product B will be what? X. That's right. So the concentration of B is X. Once we know what the concentration of A after time t and the concentration of B after time t, we can very easily find out what the rate of forward reaction and the rate of backward reaction. So in this case, the rate of forward reaction will be equal to rate of forward reaction is equal to K1 into A minus X. Let us suppose this is equation number 1, this is equation number 2. Similarly, the rate of backward reaction is K2 into X. Now suppose this is equation number 3. We know the net rate of formation of B will be equal to what? The rate of forward reaction minus the rate of backward reaction, and therefore the net rate of formation of B, the net rate of formation of the net rate of formation of B is dx upon dt is equal to K1 into A minus X minus K2 into X. Let us suppose this is equation number 4. With this, let us see the net rate of reaction at equilibrium. At equilibrium, the net rate is 0. In other words, at equilibrium, the net rate is 0, that is dx upon dt is equal to 0. Thus we have dx upon dt is equal to K1 minus X minus K2 into X is equal to 0, or K1 into A minus X is equal to K2 into X is equal to 0, or more correctly, K1 into A minus XE is equal to K2 into XE is equal to 0, where XE is equilibrium concentration of B. Okay, or let us rearrange this equation for what? K2. So K2 will be equal to K1 into A minus XE upon XE, equation number 5, where K1 represents the rate of reverse reaction or the rate of backward reaction. So once we understood this, let us see how can we get what? The expression for rate constant of forward reaction, that is the expression for K1. Substituting the value of K2 from equation number 5 in equation number 4, we get dx upon dt is equal to K1 into a minus x minus K1 upon xe into a minus xe into x. Let us simplify this. Dx upon dt is equal to K1a minus K1 into x minus K1 into a upon xe into x plus K1x upon xe into xe. When we look at this expression, we will see that certain terms in it cancels. Minus K1x cancels with plus K1x. This xe cancels with this. Okay, and we get what? K1a minus K1a upon xe into x. So dx upon dt is equal to K1a minus K1a minus K1a upon xe into x, or is equal to K1a upon xe in bracket xe minus, or here in bracket 1 minus x upon xe, or dx upon dt is equal to K1a upon xe into xe minus x, or dx upon xe minus x is equal to K1a upon xe into dt, equation number 6. Okay. Now when we look at this dx upon dt, when we look at this expression, we will see that this expression can be rearranged in such a way that the variables involving x can be taken on one side. That is known as what? The separation of variables. So when we separate the variables in this equation, we get equation number 6. And what is equation number 6? Dx upon xe minus x is equal to K1a upon xe into dt. Now this differential equation can be very easily integrated. So integrating equation number 6, we get, integrating equation number 6, we get minus natural logarithm of xe minus x is equal to K1a upon xe into t plus I, where I is known as integration constant. Let us know this is equation number 7. Okay. So on integrating equation number 6, what we got? We got natural logarithm of xe minus x is equal to k1 into a upon xe into t plus I. What is I? Integration constant. Now we can very easily evaluate the value of integration constant I, substituting t is equal to 0 and x is equal to 0 in this expression. So when t is equal to 0 and x is equal to 0, the equation number 7 becomes natural logarithm of xe is equal to I, and let us know this is equation number 8. Now how this is so? When we look at this expression, we will see that when we substitute t is equal to 0, t is equal to 0 here and x is equal to 0, obviously this term becomes 0, k1a upon xe into 0, this whole terms becomes 0. Similarly here xe minus 0, it becomes natural logarithm of minus xe, and so I is equal to minus natural logarithm of xe. Now substituting this value of I in equation number 7, we get, let us substitute I is equal to minus natural logarithm of xe in equation number 7. What we get? We get minus natural logarithm of xe minus x is equal to k1a upon xe into t minus natural logarithm of xe. Let us rearrange this expression. When we rearrange this expression, how? Taking logarithm terms involving logarithm on one side, we get natural logarithm of xe minus natural logarithm of xe minus x is equal to k1a upon xe into t. Now when we look at this expression, we can further reduce this expression, because when we look at this term LHS of this equation, we will see that this equation is what the subtraction of the logarithm of that type, log a minus log b. So we can very easily write this equation in this fashion: natural logarithm of xe upon xe minus x is equal to k1a upon xe into t. Or we can rearrange this equation for k1, and here when we rearrange this equation for k1, we get k1 is equal to xe upon at xe upon at into natural logarithm of xe upon xe minus x a into t. This is equation number 9. When we look at equation number 9, we see that equation number 9, what it is, k1 is equal to xe upon a into t into natural logarithm of xe upon xe minus x. What is k1? The rate constant of forward reaction. The rate constant of forward reaction. So In this way, we will see that the rate constant of forward reaction K1 can be very easily determined knowing what the values of T, XE and X. In other words, the value of K1 can be calculated from the known values of X, T and XE. Because A is known to us, A is initial concentration of reactant A. So how can we determine X, T and XE? We can determine very easily the values of X. How? The value of X can be very easily determined at various time intervals T before equilibrium. Okay. And when equilibrium is attained, the concentration X at equilibrium will be equal to XE. So in this way, we can very easily determine the values of X, the value of T and the values of XE. And once we know all these values, we can find out what the rate constant K1. And what is K1? The rate constant of forward reaction. Now in this way we have seen how can we derive an expression for rate constant of a forward reaction, that is K1. So let us see how can we determine K2, the rate constant of the reverse reaction. The value of K2, the value of K2 can be calculated from what? From the equation number 5. And what is the equation number 5? K2 is equal to K1 into A minus XE upon XE. So in this way, we have seen how can we determine the rate constant of forward reaction K1 and the rate constant of reverse reaction or backward reaction K2 from this expression. When we look at this expression, we will see that we can find out the rate constant of backward reaction K2 substituting the value of K1. And what is K1? K1, the rate constant of forward reaction, and the rate constant of forward reaction is obtained from this expression. K1 is equal to XE upon AT into natural logarithm of XE upon XE minus X. So in this way we have seen how can we determine the rate constant of forward reaction and the rate constant of backward reaction. With this, I hope you have understood what are reversible reactions and how can we derive an expression for forward reaction taking place in a reversible reaction and the rate constant of the backward reaction. In other words, we have seen what are reversible reactions and the expressions for rate constants of forward reaction and backward reaction. With this, I stop here. Next time, we will see consecutive reactions. At first, few examples of consecutive reactions and the rate constants, or rather the chemical kinetics of consecutive reaction. Thank you very much.